So starting off, we first have Jean-Charles Cuillandre, and then we're going to have Alan McConnachie, who's going to finish off the talk on unions, the ultraviolet, near-infrared, optical, and northern survey.
Thank you, Ken. So hi, everyone. So it's my pleasure again to give you an update today on the unions. And like Ken said, we'll be sharing the talk between my side, which is more like a general status and context within the Euclid mission, and Alan, which I'm sure, just like he did in Leiden a few months ago, in the context of the Euclid Consortium, made us all very proud to be part of this exciting project. And one of the aspects he pointed out at this stat on this wonderful stage over there, that we had this model of Gaia and Euclid sitting there, and that really, when you look at what unions came up to be, is a lot to be born from Gaia to start with as a critical element that were unique to CFHT that would complement nicely Gaia. And then, of course, with Euclid, with the need to complete the atomic redshifts. And so you'll hear more about the autonomous science that we do with unions and some elements of Euclid from in Alan's contribution. So here I take you back 3 years ago when we met in Strasbourg, and I was showing where Euclid was standing in terms of scale. And you can see that now corresponds to about May 2022. And we were planning for launch in 2023, about a year later. And everything happened according to plan. It was very, very well timed, very well prepared. And we indeed did launch in July 2023. And so since that time, things have launched. But what I wanted to point out here is like what you see on the top scale is the linear scale from all these years, from the time we submitted the mission to the time it was accepted by ESA, and then you build it over more than 10 years, and then you launched it, and now you're on this green side, to the left, to the right, in green, and so we have 6-year mission. So just for you to realize that what we're talking about, that was really from the beginning, all aimed at this survey that we are operating right now. And so, but there's been many, many, many years of preparation to get to that point. And so we have a new telescope in the sky. It works great. We had a few hiccups at the beginning where, new facility, the difference in that case at L2, you have to be very careful how you optimize and fix your telescope, which we managed to do with issue with stray light and so on and so forth. And eventually it's an amazing telescope, really. You really want this telescope to be your friend. And so it makes nice images too. And this is a plan that we're developing right now. This is a wide survey, and I love it when the plan comes together like this one. And so in this one, we have 6 years that was given by us in terms of funding by ESA to cover about a third of the extragalactic sky. And so what I did on this map here, show you in colors, in 6 colors, how you scale the various areas of the sky throughout these 6 years. So in green is the year 1. Year 1 is important because that's going to be DR1 as we know it in about a year and a half from now in terms of becoming public. But what you see, we had a bit more green and in the south versus the north. There was a strategic aspect for where we were standing with unions. But you could see in year 2 in red, quickly unions is going to gain over and going to get a lot of coverage coming up. But keep that in mind that we have also areas where we don't fully feel this red outline, which is, I'll be getting back to it. This is the red outline represents what sky is compatible with what we're trying to do with this telescope. And so since we didn't know exactly what Euclid would be pointing out, we needed to cover from the ground or guarantee from the ground that we actually do feel this red outline. It's already happening. 2 months ago, there was its first public release. It's called a quick release number 1 by ESA and from the Euclid Consortium, a lot of products. Hervé is with us here, so ask him all the details about Q1. And UNIONS is already part of it as a complementary data for the EDF nodes. So we already have 20 square degrees. It's not much, but it's really triggering this whole effort of contributing to a major mission and the science that goes with it. And Alan will be covering some of it. So it's been a long road to get to not just these 20 square degrees, but the actual 5,000 square degrees we aimed at starting in 2016. Even early on, we started this whole effort in around 2013, 2012. here I show the map in green. This is the urban coverage, how long it took us to reach today. On the lower right is today. On the top left is early 2017. And you can see the progression is not linear. It's because we had issues with the weather. We had issues with some technical aspects sometimes. But, initially we thought we would be done in 5 years. And eventually we're here today 9 years later, essentially. I'm showing this because it might be of interest for discussion with the larger surveys. It's a long road, but it was in the right direction. And so sometimes you wonder, is this still relevant after all these years? And yeah, the answer is yes, obviously. We still have a tremendous pertinence of the science we can do with the U-band and the R-band and all the complement, like Ken mentioned, that UNIONS is a collaboration of collaboration. There's all the bands happening with the telescopes. But this thing is still very, very timely and highly relevant. And so this is my chance to thank the CFHT staff and the Q team to really make things work so smoothly that eventually when you have the right condition, weather-wise, technically-wise, that you get the data for the survey. And so the UNIONS on the CFHT side for the U and R band is really building up a legacy in terms of data set. And here, we have the field of view, we have the image quality, U-band sensitivity. Those were the key element that we proposed, that we presented when we submitted the proposal. We had the SNR mode in time for the integrated coverage, and of course the LSB mode. And so we have this beautiful data set, which was tailored to exploit varying conditions. We're not asking the best conditions. We tolerated cirrus and higher air mass and so on and so forth. We modulate, we brought some modulation to what we wanted to ensure that the survey could progress at any time. That was always part of the plan. Yet, so this is a bit of a complex plot, but it shows the evolution through 9 years of the length of the night. That's the cycle you see. That's the length of the night. And in blue, the brighter blue, if you see a lot of bright blue, it means you're having a lot of bad weather during the night. That's an average efficiency per night of your observing. And so the x-axis is the number of runs since 2017, at 88 megacam runs. You feel them, Kevin? Yeah? And so 88 times megacam on the telescope. And so you make those stats and you see in dark blue, that's you observing, but you can't validate the data because they're not used good enough for the science. In green, it's data good for science. UNIONS, CFIs, as we knew it, is the red part. And you can see there were few accidents along the way. And eventually, lately, because we had the top priority and good conditions, because a lot of green, you see it on the right, miracle, like Alan was pointing out, we eventually got the data. So this amazing boost. I got just an email a few hours ago that new U-band is showing up for UNIONS. And so we're all very stoked. But that's a very important plot in the sense that it shows you a picture that it's not a clean picture in terms of saying we always get a stable number of hours per night. It varies. And so today, we also aiming as a next step, which is the next element, which is the southern extension. So that between the declination of 15 and 30. So we're adding about 30% of coverage to the current UNIONS. And that goes, the idea there was within the outline of what UK will be aiming at, it will connect with the LSST. So there's been a lot of work interacting with the Rubin community to ensure that we get to this point, but they couldn't go really much higher than plus 15. So it's already a start for them to go to plus 15. And so this is what's adding to the current LP, like Nadine was saying. We're studying about this semester or so. And it took about, if this thing is happening the way it happened for the original area, it's about 1/3 of the area. It took us 9 years. Okay, so I hope it will take 2 years just to do it, but in case, we should keep in mind maybe 3. In terms of data going to the community, there's like I mentioned, it's a collection of telescopes, so and the data processed locally for Pan-STARRS or Subaru, either at UH or in Japan, and all is collected with this very important role played by CDC. And there's a centralization of the data, extra calibration, and distribution to the whole UNIONS. So here I want to take the hats off to CDC for all the service it does for for this element. And in particular, Stephen, who does a lot of work for really bringing it together and really fine-tuning the performance of this survey. And you can see here from the element we get from Panzer's IPP or HSC pipe for Subaru, collected with what Megapipe does for Megacam, you get to this sub-percent precision over these large areas. And so, Stephen, they gave me this bit of a roadmap. This is what life happening this summer. We collecting more data, as I mentioned, and then we get all this process over the summer. All this will be blended into a grand unified catalog, which we eventually get into it, and we go to the community, and eventually later in this fall, we'll have an internal release that will become public. And so this is my conclusion. And so we've done all this work. We have now data release and so on and so forth, but we have still this important leg to go. And that's the one that we connect with the SST. And my final line is we want to make sure that we complete this fully as we've done so far. Thank you. Alan.
Thanks, Jean-Charles. Okay, so apparently I'm wearing the same clothes I was at the Euclid Consortium meeting, so that's embarrassing. Right, so I'm just going to talk about a slightly different angle, but just to come back to this point that this is a multi-telescope effort. These are all the different observing programs that have gone in, and in fact, I think I'm maybe missing a couple of the Subaru ones. So back a decade ago, we started this thing called Luau, and that was the thing that was entirely for Gaia. In fact, Luke may not remember, but he actually figured out what Luau could stand for. Because he's like, Luau has a lot of U's in it, and we want to do a U-band survey, so can we make an acronym? And Luke actually was the one who came up with it, though he's probably forgotten about that. This is a lot of different observing programs. It could have been turned down at any point. And observing proposals for just like an R-band survey of the sky in the absence of anything else. It's not a total, solid sell. So the fact that we're here now is I think, fantastic. Tremendous amount of hard work and a lot of faith put in us by various TACs around the world. The driver for the U-band, so SCSS famously is fantastic photometry, but the U-band is relatively shallow compared to some of the other bands. So the idea with Luau, which became CFHT, was to go deeper by about 3 magnitudes. So this is a U minus Gaia G, where the U is SCSS, and this is the same CMD with CFHT. And so again, the quality of the data is really quite spectacular. In the R band, I love this. This is low surface brightness processing that Jean-Charles did, compared with a Planck map of the dust. And you can see on the largest scales, it's incredibly nice. But what's even nicer is that you can go down and down and down and down into very, very small regions, and you're still able to trace tremendous low surface brightness structure in addition to the fantastic image quality that you have. At last count, as of last night, we're on 46 papers have so far come out of this. About 29 graduate theses are in progress or have been completed using UNIONS data. What I think is particularly nice is a third of all of our papers are dated this year, which I did not realize until last night. And so that really just shows the power of having the multi-band aspect, which has been a long time coming because of the huge effort of multiple telescopes. The color coding is just to kind of give you a sense. At the start, we only had the U-band, galactic archaeology, stellar populations, really strong. The R-band, motivated by weak lensing. Mike Hudson's going to talk to you about that, but they've been ramping up as papers come along. And now that we have the full sort of UGRIZ coverage, you see an awful lot of green, particularly more recently, where that's sort of the galaxy evolution science. The space-based part of UNIONS is also producing a large number of papers. So Euclid has about 19 or so papers this year so far that use very explicitly the UNIONS data. But of course, this is going to be even more in the future. So it's fantastic to see these long-planned synergies actually coming to fruition. Also fantastic is the effort put in by Stephen, who is over there, to actually corral all of the cats and to write up the survey paper, which is on AstroPH just now. And so this kind of just describes all the different observing programs, all the processing, the data quality and such like that you have with UNIONS. And this, I think, just shows nicely what you can do with it. So this is just a photometric redshift, just using UNIONS UGRIZ. This is just a first pass. Hendrik Hilderand has been leading this. This is obviously going to be improved on. You can see there's various features in the data. The point of this, though, is just based upon ground-based data only. When you look at the scatter, when you look at the number of catastrophic outliers, as per those statistics down there, you're already very close to what the specs are for the Euclid PhotoZ measurements, which combine as well into the Euclid bands. So again, this just sort of shows the high quality of the data that we have, and the fact that as a basis for both ground-based and ground space-based science, I think it's a very strong one. I'm just going to take a couple of science highlights that I really like. This is from Nick Heesters, who's currently doing his PhD with Oliver Muller. This is something very close to my heart in terms of searching for dwarf galaxies, but these are very distant or not very, very nearby dwarf galaxies, but low redshift local universe systems. When you look for any low surface brightness blobs in any survey like this, you come up with a tremendous amount of crap, right? A tremendous number of things which are not the things you're looking for, halos, stars, and such like. So when they did this search in multiband imaging, you end up with 1.5 million candidate dwarf galaxies. He then trained a version of the galaxy, Zubot, the sort of known dwarf galaxies, non-contamination, and has managed to actually come up with a very nice AI machine learning type approach to actually filter out all of the garbage. What you come up with then is some very, very nice nearby dwarf galaxies that have multi-band imaging, in fact, UGRIZ imaging. This is 45 of them. In total, we have 43,000, or slightly more than 43,000 identified at high confidence. You can look at the clustering, how they correlate with nearby galaxies and such like. So this will be really very powerful. At the Euclid Consortium meeting as well, there's other people, of course, looking for this in Euclid data. And again, just the key point here is, here we have the UGRIZ data as well. So in terms of looking at stellar populations, in terms of looking at star formation, all these kinds of things, this, I think, is going to be a fantastic data set. The paper was just accepted literally yesterday or a few days ago, so it should be appearing in AstroPH with a catalogue very, very shortly. This, I just wanted to highlight Sarah Ellison, Lee Ferreira, Bobby Bickley, Scott Wilkinson, lots of students and postdocs working on various things to do with galaxy mergers, combining with the SCSS samples. What's lovely about this is it really utilizes the R-band low surface brightness features. So you know a lot of these systems in SCSS photometry and such like, and you don't see a lot of the low surface brightness tidal features, etc. They've really been capitalizing upon this, and there's now a whole series of papers where Sarah and her team are really looking into the whole effects of mergers, what that does to star formation rates, and such like. A student, thank you, a student working with me in Victoria, Simon, has been having a tremendous amount of fun finding now really nearby dwarf galaxies, the things which are actually resolved into stars in the local group. Again, you basically just do a matched filter search, you identify all the stars, you know what a dwarf galaxy at a certain distance with a certain age and metallicity might look like from isochrones, so therefore it's very simple in a way to then statistically look through the data set for candidates. There's now, I think, 3 have been published. There's about another 5 or 6 about to be published. I think just one of them, though, that's really worth highlighting is this. This looks like a pathetic pile of garbage, because it is a pathetic pile of garbage. This is the faintest ever Milky Way satellite discovered. Those stars are, in fact, co-moving in Gaia. Their radial velocities from Keck show that they are, in fact, co-moving. When you actually work out what the stellar luminosity of that system is, it is 1.6 times 10 to the 1 solar masses. We actually think there are very strong reasons to think that this is a dwarf galaxy, i.e. in its own a dark matter halo. Even if it's a globular cluster, the question then becomes just, what? Like, how do these things form in the first place? So this is a fantastic thing for anybody particularly interested in dwarf galaxies, low mass stellar halos, and such like. And again, it just shows the tremendous power of having this kind of data set, which is roughly equivalent to 1 year of LSST, is more or less the depth that UNIONS is at. So this really gives a taster of some of the things as well that people will be doing in a few years' time in the Southern Hemisphere. I'm basically just going to stop here. One thing I just wanted to highlight is that when you're doing anything from the ground, star-galaxy classification becomes a real issue. you have a ton of candidates, but you don't actually know if the things you're looking at are in fact just unresolved background galaxies. And this is where Euclid, far more than LSST, Euclid, the data quality from the Euclid imaging is spectacular. I was blown away. And this is something that Eduardo Valbino, who's a postdoc working on OUX, he found the dwarf galaxy just in the Euclid data alone. And when cross-matched with our sample, we find that it was actually, in some sense, it was candidate 170-something that we had also seen in unions, but we had no reason to follow up candidate 170-something. But what it does mean is just the combination of the image quality that you can now do with Euclid, essentially it's megacam in space, combined with multicolor UGRIZ from the ground, be it unions or LSST. The science potential of that, I think, is tremendously exciting. So on that, I will stop other than to say that all of you are members of the CFH community. If you want to join unions, please join us. There is way more science than we can ever do. There's 200 and something collaborators, but frankly, that's not enough in terms of the science potential. If you're interested in LSST static sky science and you're not in unions, please join unions because you could be doing that science just now with these data. I will stop there. Thank you very much.
Thank you. Excellent. Excellent. Thank you. Talk. Questions, people? Yes.
Thank you. Do you have a number or forecast for the total number of objects in the union survey?
Objects in terms of just detections.
Right.
I'm sure Stevens or Ron Charles with that number off the top of their head.
Okay, thank you.
Sorry, the question was how many objects are there that BMEs has detected so far? And the answer is approximately 1 billion. So I wasn't doing that at a microphone. There's about 1 billion objects in unions.
Other question? Yep. Hervé.
It's a question maybe as much for CFHT and Q than for you. So what was the magic word that made all the last 2 semesters get so much data? Because I've been sitting in committees and trying to get you sometimes for ages, and then suddenly it happened. So what happened this semester that we need to remember for the future?
Stephen wants to answer this.
Thoughts of making your kind of conversation?
Yes.
So sorry, I can answer that because I've been watching this with anticipation. First off, the R band got cleaned up this semester in one run. And the answer is when nothing is broken on CFHT, it's incredibly powerful, very, very fast. And that's what's basically happened this semester is nothing is not working properly, i.e. everything is working properly. So the weather is cooperating, the instrument is working fine. Yeah, exactly. Don't jinx it. And then what happens, we've taken more data this semester than in the previous 5 put together. We've had data for CFIS because nothing's broken. And also because there's no competition is the other advantage. Is
This spring was also the best spring weather in about 5 years. And I can say that with a lot of authority from bad stars. But it
would be useful if we could add that Jean-Charles included. But as a fraction of the time we put that in.
Yes, and I was the thing I just want to emphasize because of the discussion that's going to be coming up later for the community surveys, it's the absence of major conflicting priorities is a massive one for scheduling. And so, again, maybe he has that plot already. He certainly wants to say something.
There's one interesting number I failed to share during the slide is when you look at that plot and the progress of unions where we're today, in total, we have 480 nights that were allocated. And in realized allocation on the sky, it's about 64% of that. So there's the allocation was not realized on the sky until we reach this regime, which has a lot to do with great weather. And everything worked indeed, like Stephen pointed out. And so it's this number. We can try to see how it evolves with time, but it's really, at the end of the day, it goes back to some discussion we had about how many hours per night you get out of your telescope. And it's not, you can't have a single average per year. It varies.
The game makes sorry. How the detection of this what they're explaining to us, and I don't know, explain us from the or actually getting the seeds, making sure
For sure. So particularly for the thing that I just showed, which is like 1.6 times 10 to the 1. So essentially the question of how low a mass dark matter halo A can form tells us about the sort of nature of the dark matter particle in terms of what is the nature of the dark matter particle. How low a dark matter halo can survive then also tells us more about that in terms of, is it a core versus a cusp? What is the temperature? Cores are not too tidally resilient as cuspy NFW type profiles. And then finally, how low a mass dark matter halo can actually accrete and accrete gas and actually form a galaxy. And then that's all about in terms of the feedback from in the galaxy formation process, winds from AGB and things like this. So that's right on the limits of both the nature of the dark matter halo and the galaxy formation, and then the nurture with respect to just the sensitivity of these very small galaxies to their external environments.
Any questions from the Zoom, Lena?
For the most part, it's three observations, but they're done usually back to back, unless the scheduling would just make them rather irregular. So in terms of the sort of cadence and the time domain stuff that you can get out of that, there's basically not very much information there at all. That could be modified in any sort of future survey. It's just, again, the strategy that we chose to take.
Okay, thank you very much.